Hello, I'm Daniel Grimmer. I'm a DPhil student in the Faculty of Philosophy at the University of Oxford. I gave this presentation about a week ago at the Foundations Conference in Bristol, and I thought I'd just record a version to post on my YouTube channel to share with people. So I'll be talking about a dynamics first view of topology, and I'll say what that is more in a second. But it involves some topological redescription techniques, which I call the ISE methodology, and which I've put up recently in these two archive papers. So, what can we do with topological redescription? Well, let's say, what if we could remove and replace the topological underpinnings of our spacetime theories, so here I mean the spacetime manifold, just as easily as we could switch between different coordinate systems. And for another analogy, what if we could do it as easily as we could change between different axiomatizations of our theory, or description with different geometric structures? So I claim that you can do topological redescription in just the same capacity by using this ISE methodology that I've been developing. But really, what scope of topological redescriptions am I offering? Let's go back to that coordinate analogy. Note that you can formulate your physics in a coordinate-free way by moving into like a differential geometric view of the theory. And from there, you could access every possible coordinate description of your theory. Inertial coordinates, polar coordinates, spherical coordinates, but also many other kinds of coordinates. In fact, most of the coordinate systems you might describe your physics in will be horrendously complicated and ill-suited to the physics in question. But we have access to every possible coordinate system. So if there's a nice coordinate system available, then it's among the things which are on offer. Right? That is the same scope of topological redescription which I'm claiming that these techniques that I'm putting forward give us. So this ISE methodology aims to deliver us every possible topological description of one's theory, most of which will be horrendously complicated, but if there are good topological descriptions for one's theory, then they exist. So I'm really offering all possible descriptions in that way. But why should we care about that? What are the sort of philosophical or metaphysical implications? I claim that if we have a strong capacity for topological redescription, just the same way we do for coordinate redescription, or to re-axiomatize our theories, or to give an alternate geometric description of them, it lends support for the following kind of dynamics first view. So let me give a schema for this view, and then we'll fill in the details. Okay? So the X, the coordinates, the laws of nature, sort of axioms, the geometric structures. Now I'm claiming the topology. Any of these you might apply this view to. So those sorts of things, they feature in our best physical theories, but given our ability to so freely redescribe them, it seems like they reflect nothing metaphysically substantial out there in the world, beyond them being one particularly nice way of codifying the dynamical behavior of matter. Now, if we take X here to be coordinate systems, for instance, inertial coordinates, right? We don't think the coordinate systems are something out there in the world. It's very clear that these are something we project onto the world in order to have a nice way of codifying the dynamical behavior of matter. They may latch on to certain features about the inertial structure of the world, for instance, but they in themselves don't reflect anything metaphysically substantial out in the world. Another example you might take is about the logical axioms that underwrite our theory. And I'll be interpreting these for this discussion as laws of nature, right? So one might think the laws of nature are something metaphysically heavy, which is out there governing the world. And opposed to that is a sort of Humean view of the fundamental laws, in which you don't take them to reflect anything metaphysically substantial in the world, beyond them just being a particularly nice way of codifying the dynamical behavior of matter. So there's this governing view of laws versus Humean view, right? And so the dynamics first view is the Humean one in this case. This line of thinking has been extended by Harvey Brown, Oliver Pooley, Nick Huggett, Simon Stevens to the geometrical structures that appear in our theories. So for instance, you can see the Lorentzian metric that appears in special relativity. You don't have to see it as some metaphysically substantial top geometric structure which is somehow tied to the spacetime manifold, and that the particles then sort of obey or survey, like they might obey a law or have to access a law to know what way to go. You can rather see there's no fundamental geometric structure out there in the world. Rather, it's just a nice way of codifying the dynamical behavior of matter, namely of rods and clocks. So I'm extending that view, that dynamics first view of geometry, to apply to the topological structure as well. So the smooth space-time topology that features in our theories, that space-time manifold, it's nothing out there in the world. That's the claim. It's not a stage on which all the players are moving around. Rather, it's just a nice way of codifying the dynamical behavior of matter. And in particular, I'm going to suggest that by offering a lot of alternatives. So I'm going to give you access to every topological redescription of your theory, sort of revealing that to be part of the descriptive artifice that we're projecting onto the world, rather than thinking it's something out there in the world that we're successfully referring to. That's a sketch of the view. I won't have time to defend that view much in this talk, unfortunately, but I'd be happy to talk about it via email or in the comments, however you'd like to get in touch. What I'd like to do instead is talk about the topological redescription techniques I'm offering you. I'll give some examples of topological redescription. I'll talk about this ISE methodology and how it facilitates these topological redescriptions. And then I'll state at least the ISE equivalence theorem, which I prove in the second paper. And it gives us the claim of scope. Right? So using this ISE methodology, one can access effectively every possible topological redescription of one's space-time theory. And the only thing which limits this redescriptive capacity we have is that the input theory and the output theory both have to have Spacetime-Kinematic Compatibility. And I'll define that at the end of the talk. But it's a very, very weak assumption. So that basically we can access every possible topological redescription of the theory, in the same way that we have access to every possible coordinate description of the theory, or every possible axiomization of the theory. It's of the same scope as those. So we finished the introduction now. I'll first talk about an example of topological redescription which we should be familiar with, which is Fourier redescription in non-relativistic quantum mechanics. And once we've established how these techniques work in this simple example, I'll move on to some more complex examples of topological redescription, where we redescribe a theory set on a lattice as existing on a continuous spacetime, and vice versa. We can go in both directions. And then I'll talk about Möbius Euclid duality, right, as another example. And then once we have these examples, I'll sort of unify them into this ISE equivalence theorem, and I'll state more generally what these topological redescription techniques can do. So here's our first example. Consider here a theory about a complex scalar field defined on a spacetime. So this is a one-particle Schrödinger equation, is ultimately what I'm going to write down. The spacetime manifold here is just two dimensions, one of space and one of time. We have the time derivative of the state here equals second space derivative with a quadratic part here. So this is a quantum harmonic oscillator. This is the momentum term, and this is the position term, right? That should be familiar. But then I've got these two non-local self-coupling terms. So the quantum harmonic oscillator I'm describing couples to itself instantaneously a distance plus and minus a away. So this is a strange sort of theory. It's a very weird non-local quantum harmonic oscillator. And we'll see why I picked this theory in a moment. But you can rewrite the dynamics of this theory using this identity here, that the shifting distance a away is the same as applying this generator. The derivative is the generator of translations for an amount a, right? And using that, you can repackage the theory here as this hyperbolic cosine. Right, that replaces these two shifts. It's two exponentials that go into that. So, as our first example of topological redescription, it's well known that non-relativistic quantum mechanics has a position-momentum duality, and that it's mediated by a Fourier transform. So if we apply a Fourier transform to the old dynamics of the theory, we get this new dynamics for the Fourier dual theory with this. So we had this non-local quantum harmonic oscillator. The time term stays a time term. The momentum term becomes a position term. The position term becomes a momentum term. And this non-local self-interaction, the derivative gets a factor of I, and that turns the hyperbolic cosine into a cosine, right, which is the new theory's position operator. Right? So this new theory here describes a quantum harmonic oscillator not non-locally coupled to itself, but rather locally sitting inside of a cosine-shaped potential. Right? So this is a Fourier redescription is one example of topological redescription, and I'll give more examples later. And in this case, doing this sort of Fourier redescription has changed the theory's character in some way. It's made it into a local theory. For instance, there's no more non-local self-coupling. So the dynamics here is local. So that's an example of topological redescription. But what is the difference between these two theories? One's first thought might be that they differ by a choice of basis. That's a very common first thought. And let me spell out what that would mean here. Your first thought might be that the common core of these two theories is about a Hilbert space-valued vector field here, where we have a new manifold of just times that the theory is defined on, and the states map those times into a Hilbert space, so an infinite dimensional Hilbert space. And then you might see that the two Fourier dual theories, or Fourier dual fields here, differ by representing this Hilbert space dynamics in different bases. There's an X basis and a Q basis, and when you represent the theory in one or other of these bases, you get either of the two space-time descriptions. So that's one way to see how this topological redescription between the theories has happened. Now that is not the perspective that I'm taking here with the ISE methodology. So I'm going to reapproach this familiar situation in a different way. But now, why am I changing the perspective on this theory? Well, because it doesn't generalize. So talk about bases and Hilbert spaces doesn't generalize to other kinds of theories. It actually assumes more structure than is necessary to get these topological redescriptions going. To mediate this topological redescription, we don't need to talk about linear theories. We don't need to talk about Hilbert spaces or bases, anything like this. The claim here, or the aim here of the ISE methodology is really to give us access to all possible topological redescriptions of essentially all possible spacetime theories. Other spacetime theories will lack this sort of linear Hilbert space structure, and so we need something more general. For instance, and I'll give an example of this later, theories about particle trajectories aren't going to have any sort of algebraic structure to them. There's no way to take a sum of states, there's no way to take a product of states. It's just a theory about particle trajectories, right? So it's not of that kind. So we don't need any algebraic structure to use the techniques I'm going to talk about. So how then do these techniques work? The ISE methodology is a three-step process. That's the initials, I for internalize. The first step is you divorce the dynamical behavior of matter from any assumed space-time background. So we sort of saw this in the move from the space and time description of the quantum harmonic oscillator to a Hilbert space description. So the spatial degrees of freedom there were sort of internalized into a Hilbert space. What we do here actually is do that even to the time dimension. So the physical fields are thought of as existing without space and time in a sort of an algebraic way. At least in this case it's algebraic, but in the particle trajectory theories we won't have any algebraic structure. But you can do a similar move. Just consider the states as divorced from space and time. Once you have this sort of space-time neutral theory, you search for the building blocks of a new space-time setting. And I call these pre-spacetime translation operations, or PSTOs. And I'll define them and give examples in a moment. But let's just see what we would do once we have them. So once you have some PSTOs in mind, you construct a new space-time setting for them where they become honest-to-goodness space-time translations. And they act on the new theory states in the right way. Now it turns out that this construction of the new theory's spacetime manifold is unique up to diffeomorphism. So given these PSTOs, it uniquely picks out up to diffeomorphism what the new spacetime manifold will be. And once we have that new spacetime manifold, you have to map the old theory's states and its dynamics and its kinematics, all of its structures have to be mapped onto the new spacetime. And you might think that there's a lot of freedom in how that part plays out, but actually, as I'll discuss, given the choice of PSTOs we've made, you have actually almost no freedom in how this part of the process happens. So the PSTOs will determine the new spacetime setting up to diffeomorphism, as well as how the new theory's dynamics and states fit onto it. It almost fixes that. So let me give a first sort of trivial example of pre-spacetime translation operations, and then I'll give a definition, and then we'll see how they work. So consider here a theory, just any theory, about some kinematically allowed states. So we have a distinction between kinematically allowed and dynamically allowed. And this could be about scalar field states, it could be about particle trajectories, it could be about sections of a tangent bundle, it could be about any sort of tensors you like it to be. Okay? Now, here's an example of pre-spacetime translation operations. Notice that any Lie group of diffeomorphisms, like an SO3, shifts in space and time, the Poincare group, any sort of Lie group of diffeomorphisms you might consider, they can be lifted to a Lie group action on the theory's states. So a group element together with a state will produce a new state. For instance, we can lift diffeomorphisms to act on scalar fields in this way by applying the diffeomorphism on the right, or the inverse of the diffeomorphism, and they act on particle trajectories in a different way. And they act via the pullback on tensor fields and so on, right? But you can generally take diffeomorphisms and lift them to act on the states. So here is a pretty trivial example. These lifted diffeomorphisms qualify as pre-spacetime translation operations because they are translation operations, right? So here is a little movie of a state shifting around in space, shifted back and forward. These are pre-spacetime translation operations, and if we pick to externalize these, then it leads us back to the old theory's spacetime setting. Okay? So that's one really trivial example. Spacetime translations are pre-spacetime translations. Okay. What is the definition more generally? Well, not all Lie group actions on the theory's states here are lifts of diffeomorphisms. For instance, you might have a group G where you give it a group element and a state, and it maps it to a new state in this way. So we have a state here and we multiply it by this Fourier factor, e to the I kappa x. So that shifts the frequencies of all the waves appearing in the theory. Now that is a way of smoothly moving the theory's states around inside of state space, but it's not the lift of a diffeomorphism. From a space-time neutral perspective, however, these Fourier shifts actually look a lot like space-time translations. If you didn't know what was space-time and what was Fourier space, you'd be forgiven for thinking these might be space-time translations. Indeed, they are space-time translations, well, not in the space-time actually, but in the Fourier space. Right? And structurally, just looking at them as Lie group actions on the theory's states, you couldn't tell the difference. And so that's what PSTOs are. They're defined as Lie group actions on the theory's states. So a group which comes with an action so that it acts somehow on the states, which are structurally indistinguishable from space-time translations. That's a sketch of the definition, and this is technically spelled out in great detail in the first two papers, 1 and 2. I give a technical definition there. So here's the second example of PSTOs. I just mentioned it. These Fourier shifts, they're structurally indistinguishable from space-time translations if you just view them as a Lie group action on the theory's states, not knowing what the space-time manifold actually is. So here is an example. Multiplying the old theory state by this Fourier factor is the same as doing the shift in Fourier space. The tilde marks Fourier transform here. But the new theory is constructed so that shifts in the old theory's Fourier space are shifts in the new theory's spacetime. Right? So these, from the perspective of the old theory, aren't spacetime translations, but from the perspective of the new theory, they will be. And we construct the new theory such that that's the case. So if we externalize these Fourier shifts, it uniquely constructs a new spacetime manifold M nu. And this new spacetime is effectively a copy of the old theory's Fourier space. It's the thing which Fourier shifts act as translations in. It's defined that way. Now that we've built the new spacetime manifold for the new theory, you have to move the old theory's states and its dynamics and its kinematics onto the new theory. But I've just said that the new spacetime is essentially a copy of the old theory's Fourier space. And it turns out there's only one way to map the old theory's states and dynamics onto M nu, up to some rescaling freedom that I describe in the paper. Basically, the only way to populate the old theory's Fourier space with the states is via a Fourier transform. Really, given some consistency requirements between the new theory's spacetime and its new states, the only way they can match up is via this Fourier transform. Okay, so we're locked into that. So again, the pre-spacetime translation operations, they uniquely build the new spacetime, here the old theory's Fourier space, and then they uniquely, or almost uniquely, populate it with states and dynamics. Okay, so from the perspective of the ISE methodology, these three quantum harmonic oscillators that we've been talking about, the non-local one we started with, the Fourier redescription, which was a cosine quantum harmonic oscillator, and the Hilbert space description. These are three different spatiotemporal descriptions of the theory. They differ not by a choice of basis, according to the ISE methodology, but according to which pre-spacetime translation operations they externalize. So I haven't talked about Hilbert spaces, and I haven't talked about bases. You just pick different pre-spacetime translation operations, externalize them, and follow what's forced from that, and you end up with these new theories. So in particular, each of these three theories will externalize what the old theory calls translations in space and time. Re-externalizing those leads us back to the old theory, which was the non-local one. If we externalize instead shifts in time and Fourier shifts, we move to the cosine theory. And if we just externalize shifts in time and leave the space internalized, then you end up with the Hilbert space description of the theory. So this is how I see these three theories as differing. Okay, so that's a first example. And now the claim is that that redescription technique of picking pre-spacetime translation operations, externalizing them, and then being forced to map the theory's states in a specific way onto the new spacetime, that is a completely general way of doing topological redescription. And to show that, I'll give two more examples, and then I'll make the general claim that this is a generic way of doing topological redescription. So inspired by the work of Achim Kempf, who says that space-time could be simultaneously continuous and discrete in the same way that information can be, he there approaches this continuous to discrete redescription via the Nyquist-Shannon sampling theorem, Nyquist-Shannon sampling theory, sorry. I approach it using this new ISE methodology that I've been developing. So in these two papers here, I show how one can redescribe discrete spacetime theories in a continuous spacetime and vice versa using these ISE techniques. So how does that work? Theories that are set on a discrete spacetime, they obviously admit discrete translation operations, and I'll show a little image of that here. So this is a lifted diffeomorphism moving this state around in space. But surprisingly, these lattice theories, they also admit continuous pre-spacetime translation operations. Now these aren't the lifts of diffeomorphisms, but they look like them structurally, in the same way that Fourier shifts aren't the lifts of diffeomorphisms, but look like them structurally. It's the exact same structural features at play here. So let me show you. These actions on the theory's states interpolate between space-time translations, these discrete shifts. Right? So here it's interpolating between those shifts, and here we can move it again to the right. Imagine smoothly moving the state around in that way. So I showed a little discrete video, but imagine that being carried out smoothly. Those are structurally identical to space-time translations when you view them as Lie group actions on the theory states. So in order to return to the discrete space-time framing of the theory, you pick out the following pre-spacetime translation operations here. So you shift in time and then the two lattice indices here. Right, so that's the way to get back to the old theory. Is you pick this Lie group, which is like R and the integer squared under addition. That's a Lie group that acts on the theory states in this way, and it looks like space-time translations because it is, and you can externalize that to get back to the old theory. Now, to move into the continuous space-time framing of the theory, you instead externalize these pre-spacetime translation operations. The Lie group here is like the real numbers cubed under addition, and it acts on the theory state in this way. So we start from the old lattice state. We still shift back in time as we did before, but now we apply a sort of continuously generated shift operation here. And these are the generators for that movie I just showed before. So that movie of interpolating between the discrete shifts in a continuous way, these are the generators for that transformation, right? And so this is a Lie group, and it acts on the theory states in this way, and I'm claiming that structurally these look just like space-time translation operations in the same way that Fourier shifts do, okay? And if we externalize them, externalizing these continuous pre-space-time translation operations, you can redescribe the old theory as existing on a new continuous space-time manifold. And the details are worked out here in 9 and 10. So the discrete heat equation, let's take that as an example, can be redescribed as continuous. So here's the discrete theory first. We have this initial state. It has some heat distributed around a lattice, and that's going to evolve in time to be a different heat distribution in the next state, okay? So continuous time relates these two discrete states in space. That's the situation. Now we can redescribe that here as a continuous state evolving in time to another continuous state. So the relationship between the initial state and the initial state here, that's a one-to-one correspondence, as is the final state to the final state, a one-to-one correspondence there. There's no approximations going on here. There's a tight one-to-one correspondence. And the nature of this correspondence is actually fixed by the pre-space-time translation operations that we're considering. So in the same way that we built the theory's Fourier space in the previous example, and then we're forced to map onto it via a Fourier transform, the same thing happens here. So we build this new continuous space-time for the theory to live on, and then when we move the dynamics over, we are actually fixed up to some rescaling freedom in how the new theory, how the old theory states sit on the new theory. Okay? And in particular, we're forced to have these new states be band-limited states, which mean they only have compact support in Fourier space. Right, so that's another example of topological redescription. You can move from this continuous to discrete setting in the same way. Now, a third example here I'll talk about, I'm going to call Möbius Euclid duality. And this one's really, really surprising that this one works out this way. So consider now a theory about a particle trajectory, right? And so it's going to map some parameter space, V nu, here into M nu. So this will be the new theory. I'll tell you what the old theory is in a moment. But the parameter space here, let's take it to be R. So we're mapping the real numbers onto the manifold. So we're picking out a world line through that space-time manifold. Okay, so it's a point-like particle. And the new space-time will just be one dimension of time here, that's R. And the space-like slices, let's call them, let's say that they were Möbius strip. So that's M here. That's the notation I use for that. So we have a point-like particle moving around on a Möbius strip over time. That's what the theory is about. And what are the dynamics of the theory? Imagine that there's a special section of the Möbius strip here in the dashed blue line. And what the particle does is it has a harmonic oscillation across that as if it's trapped in a quadratic potential. Okay? So harmonic oscillations around that midline. That's one of its modes. And the other mode in the other direction, so around the Möbius strip to rotate, let's say, it has free motion in that direction. So that's a theory about a particle on some kind of spacetime. Now, what I'm claiming is that you can topologically redescribe this theory as being about a very different kind of player on a very different kind of stage. So we're no longer going to be talking about a point-like particle and no longer on a Möbius strip. But you can redescribe it to be about something else, somewhere else. Now consider here's a second theory about a particle trajectory here, but now the parameter space is R2. So instead of picking out a world line in the spacetime, we're going to pick out a world sheet. And the new spacetime manifold, or rather the old one, the way I've got the notation set up, is, here's again time, but now the spatial slices aren't the Möbius strip, it's rather the plane. So we have a world sheet evolving in a plane over time. Now we have a kinematic constraint for this theory that we didn't in the previous theory. This extended particle must occupy an infinite straight line in the plane at each time. Okay, so at each time you take a time slice of the state, it has to form a straight line on the plane. And here are the two dynamical modes that it has, corresponding to the ones we had earlier. Pick a special point in the plane, which is this blue point. The plane can stay parallel to itself and move across that point as if it's doing harmonic motion, so in a harmonic oscillator. Right? So harmonic oscillation is about this, as if it's trapped in a quadratic potential. And if it happens to be rotating around that blue point, then it will continue freely rotating around there at a fixed rate. So that's the dynamics of this theory. Now the claim is that that's an equivalent description of the old theory. So this is a redescription of the theory about a different kind of player. We move from point-like particles to extended particles, and on a different kind of stage. We move from a Möbius strip to the plane as the sort of spatial background that these theories live on. And it turns out those are equivalent descriptions of the same thing. I don't have too much time to talk about that now, unfortunately, but you can find the details online. So we have here harmonic oscillations. These correspond to the motion of parallel lines. So parallel shifted lines in this correspondence correspond to points on the same fiber of the Möbius strip. And moving around the Möbius strip corresponds to rotating around this point at the origin. Now, when the red particle is on the blue line, or when the line is on this blue point, so when the red state is on the special blue point, right, rotation has a period of pi. I don't know if you can hear that. The ice cream man comes by and plays his song. Anyway, okay, so when the red point is on the blue point, then rotation has a period of pi. Okay, if we move around the Möbius strip a distance of pi, let's say that we come back home. So that's the period of it, the oscillation there. And if we rotate the, if we move the red point around the Möbius strip, let's say it has an orbit of pi. But if we move off of that center line, then when we orbit around, we actually have to go around twice to get back to where we were. So that when we move off of the blue line, the period becomes 2 pi. And now the same thing happens here. When the red line goes through the blue point, it only takes pi to rotate around because the line's unoriented, right? But when you are off the blue line, it takes 2 pi to come around back to where you started. So I know that's a bit of a sketch, but these theories are topologically equivalent, and in fact they're geometrically equivalent as well. You can do all of Euclidean geometry on the Möbius strip, but I don't have time to talk about that now, unfortunately. So those were 3 kinds of topological redescription, right? So we had the non-relativistic quantum mechanics redescribed by a Fourier transform. We had a lattice theory redescribed on a continuous spacetime, and we had a Möbius strip theory redescribed as being about a line in a plane. And all of those descriptions are reversible. Okay, so there's a lot of different kinds of redescription on the table, and I'm claiming that they're all done by the same mathematical techniques. So here's the ISE equivalence theorem, or a sketch of it. The setup here, what do I mean exactly when I say spacetime theory? A spacetime theory features 3 things. It has a fixed spacetime manifold, so this would be a Möbius strip over time, or a sphere over time, or any sort of manifold you'd like. It has a structured space of kinematically allowed states. So these will be particle trajectories or scalar field states, whatever kind of states you're interested in. They go into this collection S-kin of states here. And then you'll need to equip that with some metaphysically and dynamically relevant structures. So if it's a theory about a field, you're going to want to have a sum. You're going to want to have a product, maybe an inner product, any sort of algebraic characterization of your theory you need. For a theory about a particle trajectory, you won't have that, no algebraic structure, you'll have different structures instead. But whatever they are, you sort of equip your theory with the relevant structures, and then before you hand it to me to do the topological redescription. And the last thing your theory needs is it has to have some way of picking out the dynamically allowed subset of the states. So we have a difference between kinematics and dynamics, we have a fixed manifold, and we have whatever structures you need to help make metaphysical sense of your theory. So in the second paper, what I prove is that the ISE methodology is applicable to every spacetime theory of this kind. So that's basically every spacetime theory, so long as it meets a very weak spacetime-kinematic compatibility condition, which I'll talk about in a moment. And I also prove in that second paper that ISE relatedness, so whether one theory can be redescribed as the other via this ISE methodology, that's an equivalence relation. So it's reflexive, and it's symmetric, and it's transitive. Right? So it's an equivalence relation over that space of spacetime theories that have spacetime-kinematic compatibility. Right? So let me tell you then what is this spacetime. First I'll tell you the equivalence theorem, and then I'll tell you what this compatibility condition is. So the theorem says that any two spacetime theories you give me, 1 and 2, they are ISE equivalent, meaning they can be redescribed as each other, and also be redescribed as everything else in their equivalence class. So those two theories are in the same equivalence class, if and only if both theories have spacetime-kinematic compatibility, and again I'll tell you what that is in one moment. The theories have to be isomorphic at the level of kinematics. So that's the case, for instance, in the Hilbert space redescription, right? We had the spacetime, the Fourier space, and the Hilbert space description. Those are all different ways of characterizing the same algebraic content, right? But in other theories, there won't be any algebraic content and something else will be preserved. But whatever structures there are at a kinematic level, if there's an isomorphism there, and the third part is that isomorphism at the level of kinematics has to preserve the dynamics, right? So the first theory's dynamically allowed states have to map onto the second theories and vice versa. So if we have this preservation of kinematics and dynamics, and both theories meet the minimal compatibility requirements, then they are redescribable as each other via the ISE methodology. So unpacking that a little bit, what it means is that the ISE methodology gives us effectively every possible topological redescription of your theory's kinematical and dynamical contents. You fix the kinematics and the dynamics of your theory, and I will give you every possible topological redescription of that theory, limited only by a very weak space-time kinematic compatibility assumption. So any way of redescribing your theory topologically is available to us, given this weak constraint. So what is the space-time kinematic compatibility constraint? It has 3 parts. The theory has to distinguish between kinematically allowed and dynamically allowed states. So I've already mentioned that. And we have to be able to lift diffeomorphisms to act as a continuous map on the state space, right? So diffeomorphisms map manifold points to manifold points. That has to be liftable to a map on the theory's kinematically allowed states. Okay? So that's true of particle trajectories, it's true of scalar field states, it's true of tensor field states. So lots and lots of kinds of theories have this property. There must not be a direction in space-time along which every kinematically allowed state is constant. Right? So individual kinematically allowed states might be constant in a certain direction. There might be a state which, if I travel in that direction, I see this field value and then the same and the same and the same off in some direction. But it can't be that there's a direction in space-time which is trivial on every kinematically allowed state. So the formal claim is here that if I have a diffeomorphism D, which lifts to act on the state, to map it to itself, if this diffeomorphism D does this for all kinematically allowed states, then this diffeomorphism has to be the identity. The identity is the only one that does that. That's the claim. So if you meet that restriction, that you pass the second test. And the third condition is that the spacetime manifold has to be, in a sense, topologically homogeneous from a kinematic perspective. And that means that there has to exist a Lie group of diffeomorphisms that can map any point P on the spacetime to any other point Q on the spacetime, while also preserving the theory's kinematic constraints. So the theory has to map the point. The Lie group has to be able to map the point P to the point Q, for any pair of points P and Q, and it has to do so while also mapping the theory's kinematically allowed states onto other kinematically allowed states. Okay, those conditions are a bit, take a bit of time to wrap your mind around, but the point is that they're very weak assumptions. Basically, every space-time theory which has been considered since Newton satisfies these three conditions. Right? And they're very, very natural conditions. And I argue for that in the paper. So what is the key theorem that makes this all work? Here it is. Up to diffeomorphism, any smooth homogeneous manifold just meaning that it has one of those Lie groups I talked about before, which can map any point P to any point Q. So any manifold which has that property can be uniquely picked out in the following way. So you pick a Lie group G1 and you pick a subgroup G2, and you declare that G1 is going to be diffeomorphisms on some manifold. So in this example here, pick SO3. So SO3 will be the diffeomorphisms of some group, of some manifold, and it's going to act transitively, meaning it can map any point to any other point. And then you also declare that the stabilizer subgroup of that will be G2. Then you've uniquely specified the manifold you're thinking of up to diffeomorphisms. Okay? In particular, the manifold has to be diffeomorphic to the quotient of these two Lie groups. I know that's again a bit abstract, but here what it means concretely is that the only smooth manifold which has a transitive SO3 action, which has a stabilizer group of SO2, is the two-sphere. That uniquely picks out that smooth manifold. And similarly, if we take G1 to be the special Euclidean group in 2 dimensions and G2 to be the special orthogonal group, then that uniquely picks out the plane as the manifold we're talking about. Right? And finally, if you take SE2 as G1 and the one-dimensional Euclidean group as G2, that uniquely picks out the Möbius strip. So there's a way of picking out smooth manifolds uniquely by declaring certain groups act in certain ways on them. That's the key theorem that makes all of this redescription work. So, hopefully you've kept on till this point. In conclusion, I claim that the ISE methodology, especially given that ISE equivalence theorem that I just mentioned, that it allows us to remove and replace the topological underpinnings of our spacetime theories just as easily as we can switch between different coordinate redescriptions of our physics. And to me, given how easily we can redescribe this aspect of our physics, it seems to me that the spacetime topology is more of an aspect of how we represent the world rather than corresponding to anything which is out there, right? A stage upon which all the things happen. And hence, what I advocate for is a dynamics first view of topology, that the topological structures that feature in our best physical theories reflect nothing metaphysically substantial out there in the world, beyond them being one particularly nice way, among other options, of codifying the dynamical behavior of matter. Okay, so final thoughts. Where does this leave us? I see roughly 3 options for where to go. We could adopt a sort of deflated realism, meaning we could be realists about space-time topology in the same way that David Lewis, for instance, is realists about the laws of nature. So he thinks the laws of nature aren't anything that governs the world, they're just codifications of dynamics or of the Humean mosaic. But nonetheless, there's an objective and mind-independent fact about what the best way to codify dynamics is. And that picks out, in an objective and mind-independent way, what the laws are. And therefore the laws, while being just codifications, are still real, objective, mind-independent parts of the world. And so perhaps there's an objective, mind-independent fact about the best way to topologically codify the dynamical behavior of matter. That doesn't mean that there exists a space-time stage upon which everything moves. That's what's being denied here. Rather, the space-time manifold is just a codification of dynamics, but it's the uniquely and mind-independently best way of doing so. So it's still real and objective in a sense, but it's not metaphysically there. It's not metaphysically substantial. So that's one kind of response. You could adopt A second kind would be a conventionalism about space-time topology. There's a lot of talk about conventionalism about geometry, which goes back to Poincaré and others. But perhaps the process by which we come to have a topological picture of the world, perhaps that has some non-trivial aspect of conventionality to it. Right? Then there would be a sort of underdetermination of the geometry, which is only fixed by, or of the topology, which is only fixed by a conventional stipulation. And the third route, which is possible, is that we could be neo-Kantians about space-time topology. So perhaps instead the process by which we come to have a topological picture of the world is a matter of a priori intuition. It's something that's inbuilt into all of us, and in fact it's a necessary condition for cognition to even begin. That's another option for how to proceed from this point, and I'll leave it to you as to which of these three options is most appealing. But here are the references for the talk, and thank you for your attention.